Hello, welcome to the Wastewater Nutrients Process Control Testing Series. Today, we'll be talking about nitrates. My name is Nick Willis. I'm a Senior Program Manager at the Environmental Finance Center at Wichita State University. So the agenda today is that we will discuss why we would want to test for nitrates at our treatment plants, where to test for nitrates at the treatment plants, and then how to test for them. So why are nitrates an issue with wastewater treatment? First, nitrates are a public health issue. They are problematic in drinking water. The maximum contaminant level for drinking water is 10 milligrams per liter of nitrates. So we're seeing more and more regulations at plants that discharge where there's a downstream intake. So if there's a public water supplier that's withdrawing out of a downstream lake or a river, we are seeing more nitrate related limits for them. The limit is often as nitrates, or it can also be part of a sum of nitrogen compounds in your wastewater. So you might see it as total inorganic nitrogen or total nitrogen. Nitrates in many cases will be the bulk of either total inorganic nitrogen or total nitrogen. So nitrates can sometimes dominate the nitrogen species at your plant. A lot depends on how you operate it and some other characteristics of the wastewater, but nitrates is a hard one to ignore because if you have good ammonia removal, your plant at some point in the process will have high levels of nitrates in it. If your plant is discharging nitrates, this is often an indication that there's good opportunities for energy savings that can be realized. So with better air control and or cycling of air on and air off in some of the aeration basins, we can see significant reductions in the amount of energy used on both aeration and mixing at the plant. Also, if your plant is designed to remove nitrates with an anoxic zone, testing for nitrates in that anoxic zone is a good indicator of whether or not that anoxic zone is functioning well. So you may have to modify operations, possibly add carbon at some place in your plant to have that anoxic zone work correctly. Finally, if you are required to remove phosphorus as part of your permit process, the presence of nitrates will inhibit anaerobic fermentation that is required for biological phosphorus removal. So if you have a lot of nitrates in your plant and that nitrate-rich water is hitting your anaerobic zone, and it can happen because of return flows of either the mixed liquor or even high levels of nitrates in your return-activated sludge, you can inhibit that biological phosphorus removal. So having low nitrates is basically a prerequisite for having good biological phosphorus removal at most plant setups out there. So where do you want to test for nitrates? For most plants, you're going to be testing at the overflow of aeration basins, so your aerobic basin. You'll also be testing return flows to anaerobic basins or anoxic basins, depending on how your plant is designed. And you maybe will also be testing your sludge decanting and dewatering for the presence of nitrates returning to your plant. There are some special cases out there. If you are a batch discharger, you may want to test for nitrates as a process control before commencing that batch discharge in order to ensure compliance. You may also want to test your influent for excessive loading or spikes that are seen elsewhere. Most nitrogen in typical wastewater, however, is in the form of ammonia that's coming from humans. There are some, exceptions to the rule, as always. Perhaps there's an industrial discharger with high nitrates. I have seen this with some food processing. Nitrates can be used as a preservative in, for example, processed meat applications. So you could get high nitrates that way. Likewise, pretty unlikely, but you may see something like fertilizer disposal, washout of fertilizer application tools and bins and basins that could lead to high nitrate in your plant. I would expect something like this would be seasonal and would be a little more difficult to track down, just because fertilizer applications are not consistent year round. So how do we test for nitrates? There's kind of three broad manners to do it. So there's test strips. These are pretty cheap. You buy a little packet of them. And you use them, you dip it in the water and typically you wait for a certain amount of time. These can be pretty suitable for daily process monitoring. It kind of depends on what you're monitoring for. If you're just monitoring for compliance or making sure that various steps in your process are working well, test strips could work. Similarly, color wheels, similar to test strips, and that it relies on a color change and then an operator to interpret the results with a color wheel. This can be suitable as well. However, most plants would benefit more from having some sort of a digital colorimeter and spectrophotometers. I have seen nitrate specific colorimeters out there, but most of them will be a broader array of various constituents that could be important to test for at a treatment plant. The advantages of these, while they are more expensive, they are more accurate as well. Many people are colorblind. Some people don't really know it very well. So you avoid issues with color blindness that do crop up with color wheels and test strips. You are likely to need something a little more accurate if you have really stringent limits on your plant. So depending on the driving forces for nitrate removal, the colorimeter or spectrophotometers that give a digital readout are probably better suited. Many of these test apparatuses can connect to a computer, so you can pull down the information really easily. You can store past tests. There's time and date in some of them. A lot of benefit for record keeping in this. It is also easier to dilute since you take the sample out at your plant, say at an aerobic overflow, and then you bring it into the laboratory. So laboratory techniques of dilution typically are a little easier. For some nitrate tests, you may need dilution. Some other ones, maybe not. Whenever you're looking at tests, always look at the test range and also interferences on them. I believe there's some nitrate tests that interfere with higher chloride levels. So if you have higher chloride levels, really pay attention to the interferences on your nitrate test. So I'm now going to run through some examples of plants that I've worked with in Kansas and where we might want to sample for nitrate. So the first one is a sequencing batch reactor. This is a 2-cell system in Ellenwood, Kansas. I will note that there's an equalization basin before the UV lights. So if you're looking at troubleshooting here, sequencing batch reactors basically are a treatment plant in a basin. So everything you need to process the treatment water is in a single basin. So it's aeration, it's mixing, it is settling, it is decanting. So think of it like an activated sludge treatment plant in a single basin. It does all of those. So it goes through a various cycle. For troubleshooting purposes at an SBR plant, you might test for nitrates within the batch cycle. So maybe before and after your anoxic program. So that anoxic program is where you are going to turn off the air, likely turn off some of the mixing, if not all of it, and really run that oxygen level down to the point where it's anoxic and the nitrate is removed by denitrifying bacteria and turned into nitrogen gas. So you can see how well this process is working by testing for nitrate levels before that program begins and then at the tail end of it as well. With sequencing batch reactors, you also want to ensure that your various reactors are working properly. So one reactor may be working really well and another one may not be. So looking at the comparison of the performance between reactors, you'd typically be sampling each basin's decant. And then you might also want to sample near the UV lights because that shows it's basically a composite sample at that point because of the equalization basin at this facility. So now we're going to move on to oxidation ditches. This is a pretty common setup, pretty simple plant here in Buhler, Kansas. For troubleshooting, many of these ditches are run with either specific zones. So we have a lot of facilities that have modified their rotor operation. The rotors are what you see on the ditch crossing horizontally. You can see one of them is for providing air. The one that is kind of on the northeast, it's the one on the right and higher up in the picture. So that is providing air. That will be the aerobic zone. And as the water flows around the ditch, the oxygen levels decline, eventually forming an anoxic zone where the nitrogen is, where the nitrate is removed. So in this operation, you would want to sample at different places. You would expect high nitrates where you have that rotor on, where you are seeing the ammonia be nitrified into nitrate levels. So that would be a good indicator that that process is working well. And then you would also want to sample at the lower oxygen levels of the ditch in the anoxic zones, or some plants are even able to run anaerobic zones in these single ditches for the presence of nitrates to figure out how your ditch is performing, because it's basically not uniform throughout it. You might also do it if you are running both rotors and are cycling air on and off, at which point you would look at the nitrate level towards the end of the air on and then towards the end of the air off. In this case, you'd probably be looking at the oxidation ditch overflow, allowing the mixed liquor to settle out, and testing the supernatant. Now, there's many plants that operate parallel plants. This one is in Edgerton, Kansas. It is a Schreiber system. When you're looking at nitrate levels in parallel plants, first you need to identify for yourself how parallel the plants are. Some systems are set up and they share a return activated sludge line. So the plants are not truly independent. Other ones have separate return activated sludge lines, in which case they are more an independent plant where they operate separately from another. Operational changes can also add additional flow or loadings to one of the plants or the other plant. So you need to understand how that's going. With this, for troubleshooting for nitrates, these Schreiber plants basically have aeration and anoxic cycles. So you would be testing the nitrate level towards the end of the aeration cycle and then towards the end of the anoxic cycle to see what the nitrates are at their highest and then what they are at their theoretical lowest point. You'd also be looking at testing any basin overflow in a plant like this before it's going to the clarifier. Now we're going to move to a biological nutrient removal plant. So this is a plant that's designed from the ground up with separate anaerobic fermentation zone and a separate anoxic zone. So the anaerobic fermenter is where we grow our biological nitrogen, our biological phosphorus organisms. So we ferment those there. Then the anoxic zone is where we direct some of our mixed liquor that's high in nitrates to an area with low oxygen levels. So troubleshooting nitrate sampling here, you probably want to be looking at the exit of the anaerobic fermenters. Basically, you should have almost zero nitrate at that point. Depending on internal recycles, you may have some, and nitrates may actually be inhibiting the anaerobic zone and the biological phosphorus accumulator organism growth. You'd also want to look at the exit of the anoxic zone. Most BNR plants like this are directing nitrates to the anoxic zone, and it's in that anoxic zone where the nitrates are removed. So if you have nitrate levels that are high coming out of your anoxic zone, that's an indicator that something is amiss with the anoxic zone. You also want to be looking at the exit of the aeration treatment basin in this scenario. So water is directed to the anoxic zone. It comes back out to the aerated treatment basin before going over a weir to the final clarifiers. So this is basically the nitrate level that will be exiting your plant. You'll also want to be looking at the return activated sludge, the levels of nitrate in that. This is particularly important if some of that return activated sludge is going to the anaerobic zone, which in many plants it may be, because that can interfere with your biological phosphorus removal efforts. Finally, you want to look at those return flows to the anaerobic zone and the anoxic zone. The anoxic zone in these plants work, again, by getting some of the mixed liquor where ammonia removal has occurred and bringing the oxygen down in that mixed liquor and having denitrifying bacteria consume that nitrate. For this plant, it also has an effluent storage pond, and there's many facilities that have something like this or a polishing pond. It would be important to understand what the nitrate levels are in that pond if you're using it for discharging. Some plants may use this for beneficial reuse, irrigation of a park or golf course or something like that. At which point it may not really be necessary information to know. But if you're looking towards a more sustainable operation, it is important to understand and have the superintendent responsible for that irrigation system understand what levels of nutrients they're receiving from that wastewater reuse. Perhaps they can cut their fertilizer bills through use of that reuse water. We're now going to move to an activated sludge plant with primary clarifiers. This is here in Kansas City, Kansas, plant number 20. Here, you're really going to be looking at the exits of the aeration basins, and it's going to be every overflow from an aeration basin because each one of these could have different factors that are leading to successful nitrate removal or unsuccessful nitrate removal. Many plants like this have been retrofitted for cycling of air on, air off. And it's important to know if that is, effectively removing nitrate in the wastewater with the air on, air off operation. You'd also be looking at the exit of both clarifiers. And with a setup like this, it's really important to understand if you're a drop of water, are you going only in one path through the plant, or are there splitter and control structures that you could end up in either final clarifier or either aeration basin? So that can also be important for troubleshooting, is to understand the flow pathways of water through your plant. There are other tests for nitrate removal that may be beneficial. So ammonia. Low nitrates in your wastewater can be caused by both effective biological nutrient removal and ineffective ammonia removal. So if you are having high ammonia levels, I would generally expect the nitrate levels in your plant will drop. And the reason for that is because that nitrate conversion is never being done. So you're keeping your ammonia in your plant. Make sure that ammonia removal is occurring. Don't declare victory on nitrate removal if you're really having a failure of ammonia removal at your plant. Biochemical oxygen demand, or if you use the proxy chemical oxygen demand, biological nitrogen removal requires sufficient BOD for the organisms to thrive. So if you have a carbon-starved system, you won't have nitrate removal occurring. pH. pH is important for wastewater treatment. And when it comes to nitrate removal, it needs to be above about 6.7 or so for ammonia to be converted to nitrates. So keep in mind that you get nitrates from ammonia being converted to nitrate. So if you have ineffective ammonia removal, you won't have nitrates. You'll probably have permit violations for ammonia levels reaching your receiving stream. Alkalinity is important to nitrate removal for the same reason, because ammonia consumes alkalinity. So when you convert ammonia to nitrates in your plant, you expect alkalinity to decline. If you do not have sufficient alkalinity, you can't get the whole nitrogen cycle to occur in your plant. We also want to look at various sensors here. So a dissolved oxygen sensor is an okay way to look at the anoxic conditions that are needed for nitrate removal. So remember, ammonia being converted to nitrates requires an aerobic environment. So a dissolved oxygen sensor is really good at pegging that. So if you have 1.7 milligrams per liter of dissolved oxygen in your aeration basin, you're probably good. Some plants will run higher than that. Some plants are lower. Oftentimes you'll hear 2.0 being discussed as a reasonable target. Now, the anoxic conditions that are required to remove nitrates require very low DO. And I would tend to recommend that a plant is going to be better off using an oxidation reduction potential probe to monitor that wastewater environment for nitrate removal than a dissolved oxygen sensor. I've seen plants get by just fine with dissolved oxygen sensors. I understand there's limited budgets, and more sensors require more time and more effort, but that oxidation reduction potential probe can benefit you on nitrate, and it really benefits you on total phosphorus at your plant. If this training has been helpful to you and you're having nutrient removal issues at your plant, and you treat less than 1 million gallons per day, which on average, not the design flow, feel free to reach out to me. I can try and provide you good information. We can work up some sampling plans for your own facility. Best way to contact me is by my email address listed here. Otherwise, you can call my direct line at the number listed below. Thank you for your time and best wishes in your nutrient removal efforts at your plant. Thank you.